Yeah, I hope this on Mock-Theta functions, and I will just introduce the major problem which was and how Ramanujan keeps coming up in different contexts and continues to be of relevance. So it will be more of general thing than particular thing. So I will again apologize myself for laziness as my colleague Amit did, but this is in the other way. I couldn't find time, so I have not put down a lot of formulas. So, okay, the extraordinary friendship, as is well known, between Ramanujan and Hardy began and ended with two very important letters. The first one, of course, which is famous, I beg to introduce myself as a clerk in etc. was dated January 16, 1913, about 100 years ago, a day after Pongal, is too well known. And his last letter was again in January, written on January 12, 1920, a few months before he died. He died in April. And in that letter, Ramanujan said that I am extremely sorry for not writing to you for a long time. And then he went on to say, I discovered very interesting functions recently, which I call Mock-Theta functions. They enter into mathematics as beautifully as the ordinary theta functions. And I am sending you with this letter some examples. And he listed 17 examples, which he classified into 4 of order 3, 10 of order 5, and 3 of order 7. Of course, there was no mention of what order meant. There were just some series. Okay, and this was the thing. And then people started looking at it. So it's like, somebody gives you a set of numbers and say these are very beautiful numbers, they have a lot of beautiful property, and does not tell you what beautiful property they have. Then how do you go around looking for the property which is beautiful and shared among this handful of numbers? That is the problem. So the problem for now mathematicians was, what is it that is running through these 17 examples, and the only hint that comes is this order 3, 5 and 7. And fortunately for us, he told which are of order 3 and which are of order 5, otherwise it would have been totally chasing this thing. So that was the problem which the world confronted. And he gave these examples and wrote down some relations, which are very simple ones you will see later. Okay. So this is not a highly informed lecture on Ramanujan's Mock-Theta function, but I hope to convey to you some points about its journey from Ramanujan's deathbed, so to speak, to a very active area of research, embracing more and more subject as it goes. So sometimes it's a meta talk or a mock talk, you can call it. And the most recently, it has had applications in black holes in string theory. So that's the sort of thing. So G.N. Watson was among the first persons to work on these functions and identities contained in that last letter. In a lecture aptly titled The Final Problem, an account of the Mock-Theta function, he presented his work on it. So yeah, that final problem has reference to Sherlock Holmes, and so he being Watson had to. So all these connections are there. And he concluded saying Ramanujan's discovery of Mock-Theta function makes it obvious that his skill and ingenuity did not desert him at the oncoming of his untimely end. He still was. He was suffering very much. He was vomiting blood. He was not able to eat properly, etc. And he was and to his students, such discoveries will be a source of delight and wonder until the time shall come when we too shall make our journey to that garden of pines, which is the garden of ever-blooming flowers, supposed to be. Okay, so what did that letter contain? Yeah, this is the one. So just as an example, his first order 3 Mock-Theta functions were denoted by f, phi and psi, and this is the left. This is as in Ramanujan's. He writes for the handwritten note, and this was of course text. So he gave this kind of things, and then he gave a relation, and it just went on in that vein. So he would list order 5 and then say these are the relations between these functions, and would go. So now the question is, then how do we actually get the definition out of this? He of course said something about their asymptotic behavior, that they agreed with theta functions at all roots of unity, etc., etc. So the first thing that Watson did, for example, was to look at these definitions and give the proofs of these identities at the end. Okay, and then later, of course, in retrospect, this is the present day conclusion. The RHS is a modular form of weight half, but for a factor of q power minus 1 by 24, which is okay. So the problem, I hope, is clear to you. His letter just listed 17 examples, relations between them, some of them he called odd, etc. Now the world was confronted trying to find what he meant by Mock-Theta functions. That was the thing. So unlike many people think that mathematics is a man-made universe, everybody knows what one is talking about there. But this is like, yeah, the moon is going around the earth, what makes it go around? So you go on trying to find gravity, this, that, etc. Similarly here, there are 17 examples given by Ramanujan, so let's say existing in nature, and now you have to see what is it that is connecting them and how to prove those relations. So the connection with theta functions is this expansion, and they all look similar, but the theta functions were famous because of various algebraic relationships and things like that, and that was the problem. So this problem, as I said, first Watson looked at this and gave proofs of this identity, this 2 phi q minus fq is equal to f of q plus 4 psi q. This itself is not easy to derive. Then the other identities proved even more difficult, but nobody could find out what his idea of Mock-Theta function. Everybody had some suggestions, but nobody had. Then some people had found a couple of other similar series and relations among them, and have been going around like that, and they said, okay. So the breakthrough finally came in 2002. Don Zagier's students, doctoral students, Zweigers, he found at least what we think is the final thing. So what he found is the current day thing, and it relates that to modular form, and what actually Ramanujan refers to as theta functions are actually modular forms, and so what he called Mock-Theta functions are modular forms in the present day context in the thing. So that was the thing, and this is intriguing. How did Ramanujan think of those things, and what properties he visualized, envisaged, etc., etc. And this Mock-Theta functions is another, so which was thought to be not in the mainstream of mathematics, etc. But they are not only in the mainstream of mathematics, but also go into present day physics, string theory, and various other contexts they come up. So that's the point I wanted to say, and the Zweigers' work was the real path-breaking thing. So our 1920 was Ramanujan's list of examples and the first occurrence of that Mock-Theta functions, and Zweigers in 2002, after 80 years, was able to actually find a definition of Mock-Theta functions. And with that, after that, the beauty of that was once you relate it to modular forms and all, the point is you get nice structure into that. So these functions actually become elements in a vector space, and they will have finite dimension and things like that, and therefore these identities like this will follow from that, those algebraic relations. So what was very difficult earlier, it took, this inspired lots of thesis. Somebody would say, take this, for example, this was Watson's paper, and then he proved these relations, etc. And some other relations were there in Ramanujan's original work, I did. And they looked at Ramanujan's last notebook when it came, that contained many more results, which people thought they discovered, but they were already in Ramanujan. When the last notebook surfaced, they discovered that identities which people thought they discovered afresh along these lines were actually already contained in Ramanujan's notebooks. And that relations which were extremely difficult to prove, something like this, just on the basis of this definition of that infinite series is a fairly challenging thing. And these are the simplest among the relations. The remaining ones are quite complicated, and they required some superhuman effort on the analysis side. But once this Vegas thing came and he related it to known objects and an algebraic structure came into that, those identities now follow very beautifully. So that's the point about theta functions. Theta functions again have infinitely many coefficients. Again the problem is same. What Amit talked about is the same. So you have large amount of information which will giving you a particular conclusion. Now you want to say, I can't go on accumulating this information to draw this conclusion whether somebody has diabetes or not, because by the time you actually do all the computation, this man may have 10 years may have lapsed, so it's no use. So the idea is to see, okay, I want to do some computation so that by instead of looking at million, by looking at 10 or 15, can I conclude something similar. So the point about the structure is that's what it does. So instead of analyzing everything and enormous analysis and other kinds of efforts going into proving such identities, once you have this structure and you know the definition of modular forms, these identities followed fairly easily. You don't have to have infinitely many computations. By doing finitely many computations, you can conclude whether two infinite series are same or not. That's the point. So you have one infinite series coming from one side and you have another series coming from another side, and Ramanujan says these two are equal. So one way is to check each coefficient and do, which is never ending process because both are infinite. So the question is there some way we can say you can. So that's what modular forms, that structure will imposes on it. It says this is both these series are examples of modular forms, which is some 10-dimensional space. Therefore, if you compare the coefficients, let's say first 50 coefficients, and if they agree, they have to agree everywhere. It's like polynomials. That's the kind of question. If you have two polynomials of degree n and you know that at some n plus 1 points they coincide their values, you can conclude the polynomials are same, right? You don't have to check them at each point. That's the thing. So if you know they are polynomials, finitely many are enough. If you know they are infinite series, then another structure. So the beauty of Weger's work is that he was able to identify that structure beneath these 17 examples, and that's one of the high points of research. And once that he did that, then people were able to give more such expressions. Because now it is just a question of playing around. You just take, it's like in a vector space. You just take known examples, take linear combinations, and see if you can get interesting things about that. That's the point. So I don't think I'll have. Yeah, this is the, I just wanted to say the classical theta functions, because that also I mentioned in my talk, is due to Jacobi. Again, Jacobi did not say define or anything. He just gave an example because he wanted in number theory. Yeah, in number theory there was a problem he was attacking, that every number can be written as sum of 4 squares, and then he proved that result by considering some infinite series and its transformations, etc. And that has many other avatars. For example, the theta function has as a sum is written like that. There is a bracket missing on the other side. And then it also has a product expansion. So Jacobi went from the application that he has to show that every number can be written as sum of 4 squares. Then he used an infinite series which is defined like this. Proved transformation properties using Fourier analysis and all that. And then later people thought it was an interesting thing and kept on studying, and they came up with product expansion like this, etc. Okay. And now with the Ramanujan thing, it is the other way around. He is telling you that, see, that theta function when you try to expand will also have some denominator like this if you look at that. Okay. And now this is the other way. So now Ramanujan has given the product expansion. Now you have to see what it is like and what are the applications. So Jacobi's theta functions came from the applications to theta functions and various properties it satisfied. And in the Ramanujan Mock-Theta function case, it is completely the other way. He just listed down some examples and then the expansions, and now you have to see what is that underlying structure and what are the possible applications, etc. And now that circle is complete. You have a definition of a Mach modular form, which we hope is what Ramanujan had in mind, because all the statements he made in that and all the statements that are seen in the last notebooks are we are able to prove that. So this is what mathematics is about. It's not that it just has some see the general impression is that the final things come first, as we say. I mean, we state a theorem and then give a proof, etc., etc., but it's actually the other way. You have lots of stray examples, then you see a common thread running through them, then you take that and call that the definition, and then you say observe some more properties of that which figure into theorems, etc. But the way the mathematics is learnt is the other way. So you have to learn to go back and forth, okay, which is again was what was reflected in the other earlier thing. So this is all I have to say about Mock-Theta function and Mock modular forms. Anything is going to be more technical. If people want some particular thing, they can ask, okay. But now I want to close with a few remarks, again inspired by the previous talk of image processing and again because of what I said earlier. What could it mean for technology relevant to us, that all this singular value decomposition? See, the problem is of trying to get information about some situation with as few parameters as possible. That is all what is one is looking for. So the results are from, I mean, the examples are from various. You want to know whether it will rain tomorrow or not by measuring temperature, maximum, minimum temperature, humidity, and practically any other thing you could do today. If you can do that, then you can predict weather. Okay, so that's the whole game. So here is the image also. Image, if you take a very good image, high pixel image, etc., then the size becomes very large. So you want to send it over wireless networks, etc., it's going to take time. So the idea would be, okay, is it possible that I give less information, but I'm able to recover the image, full image back later? So that's what. So that's the point about this. So if you take 10 approximations and you can sort of more or less get the idea of the image, that would be. Of course, you can't use that for printing, for example. It will be very, very edgy. Okay. So the whole game is that, and that's where the mathematics has that role. It is that it transfers a problem from the real world into the mathematical this thing, and then you solve the mathematical. You have got a mathematical model and you do things. It could be a graph, the model could be a differential equation, or the model could be any of these kinds of Mock-Theta functions, Mock modular forms. Then you do some mathematics on it, then you transform. So like the image is represented a matrix, and once you have a matrix, we can do lots of things with it. We can, as I said, singular value decomposition, we can find its eigenvalues, we can find eigenvectors, various things. But what do they mean back in the real world? Suppose I find an eigenvalue here, what would it mean to me in the sense of the picture that is there? So you solve them. It's a game which goes on. You start with the real world situation, get a mathematical model, then from the mathematical model you get things out of it because you can work. For example, you get a Fourier series, you neglect lots of terms, only take few, and then you read back it into the real world, what it means. So practically everything is that. So the sampling is a general technique. One wants to apply it in a abstract setting, because you see, you can always take some images, remove all redundant information, unnecessary information, what is called noise, and get a small thing out of it. That's what cartoonists, for example, do. I mean, they take this image of Gandhi and with a few lines, they're able to convey to you it's Gandhi back again. I mean, it's a very simple picture, you know. But what these people trying to do when you are studying abstract thing is to be able to do this in a very general way. This takes an artist a long time to imagine what are the lifelines of in a Gandhi picture and then capture it and put it. So to be able to do it in a long this thing, where you have to really abstract it and see you can. And why they work, there is no explanation. It's what Eugene Wigner called the unreasonable effectiveness of mathematics in physics. You do this, so like he says, you take 10 approximation, you get a matrix. If you have one matrix, you take some singular value 10 approximations, you get another matrix, and you look at the image represented by this matrix, and lo and behold, it looks like the original image. So you are done. There is no explanation as such why it does. It is just that it happens. That's it. So the many a time I found in engineering colleges also, so when students ask this question, There's a mistaken thing that they are asking but actually what they are asking is a simpler thing. So that always reminds me of a joke. Apparently these Russians, when they learn to speak English, the one problem they have, even Indians, is with the articles, the, a, an and all. We leave it off. We don't realize that there. So once this Russian who had emigrated to States, he was working in New Zealand, wanted to know time. He did not have a watch. So he asked a professor of philosophy department. He didn't know he's from the philosophy department. He was just working, he asked him, what is time? So that man said, oh, it's a very difficult question. But this man, what he wanted, what is the time now? So most of the thing is the engineering students, I find this was the problem. They come with very big things saying that they are not able to do, and all they need is this clearance. They don't, when they ask, why is it that, sir, this, when I take the Fourier transforms, I move from the space domain to the frequency domain. There's nothing there. It is just that we think it happens and you come back and it works. That is all. When you move from the time domain, space domain to the frequency domain, then you neglect a few coefficients and come back, and lo and behold, you have your audio thing with some filtering. So now you say because of that some high frequency things are chopped off and you are getting something nice. So there is no explanation as such. It just that it works. That is the thing. Yeah, I think because of time, these things I will not go on. But if there are any remarks or questions, etc., I would be happy to answer. So I just end with a small story because that also captures this. I mean, that story I read it in a different context. See, this father came home and he had done something with the map of the world. He had made many marks and all, and he had left it on the table. But his young son didn't know he wanted to do something with that, so he took that sheet of paper and did various things, cutting it at various places. When the father came back, he said, angry, and he said, what is this nonsense? You have torn this into pieces, and I wanted that. It contained very nice information. And I said, go and get me. So and 1 hour later, this son went back to him with that map of the world with all this properly done. Father was very amazed. He said, how did you manage? I mean, I never knew you knew what the world looked like, because he had all the countries and all it's like assembling a jigsaw puzzle, and he had assembled it correctly. I was very happy with the son. I said, how did you manage to do it? Then the son turned over the page and showed that there was a sketch of a cartoon of some cartoon thing, one of those cartoon characters, simple drawing. He said, I just put this together, this cartoon man, and the other thing turned out to be, this thing was, he did not know the world. So similarly with mathematicians, we don't know exactly why it was. You give it to us, we find some such other thing which is hidden, and we assemble that, and lo and behold, the front page gets properly done. So that's what one is trying to do. Yeah, there it was used to illustrate that if the man is set right, the world becomes right, but that moral is not important. The image processing model was important. Yeah, and lot of work which is on that direction will help us a lot in the optical character recognition, because that's again the same sort of thing. The idea is, with little information, can you recover all the other data? And in this context, let me also say with one small example. For example, one of the students came to me and said, there is this doctor, this you would have also heard, who feels your pulse and tells you every other vital status. He tells you your ECG, he tells you your blood pressure, heartbeat, everything. Is it possible? So I gave him a mathematical scenario. It is possible. See, the thing is, the pulse, let's say, depends on some 50 parameters. Blood pressure, the temperature of the day, his heartbeat, humidity, many other things. Okay. So if you know all those parameters, and if you know how this pulse depends on all this mathematical relationship, you will be able to compute. Now the thing is reverse. You have one number and you have to recover these 50 different parameters, which is giving rise to this number. But what could happen is, this person by practice knows that the possible values of pulses are these few, and these parameters, these 100 parameters will lead here, this will lead to this will lead. So by practice one may be actually be able to recover that detail. It need not be 100% thing. It's just that he knows that these parameters within this error will be able to give you only this pulse value. So if the blood pressure was outside this range, this pulse will never come. He knows by experience. So it is possible. So it's always the question of knowing a lot by rather concluding something by knowing very little information about that. Okay. Thank you. So I leave it to you to conclude a lot of about Mock-Theta functions by whatever little I have told you so far. Thank you. And if there are any remarks,
any questions?
Did Ramanujan know about modular form?
Yeah, no, in the sense he did. Because, see, I will tell you the small irony because many people might not be familiar. Of course, mathematicians are familiar with this. The problem is Ramanujan wrote to many mathematicians about his results. In fact, one of them was Erich Hecke and another is Hardy. And that was the First World War time. So communication between Germany and England was not happening very well. And Ramanujan was a mathematician more along the lines of Erich Hecke, who was working on modular forms at that very time. Hardy actually is an analyst, not a number theorist. So the analytic aspects of Ramanujan's work was what appealed to Hardy. The infinite series, manipulating them, etc., etc. But the fact that they had number theoretic underpinnings was not known to him. That was known to Hecke. So if instead Ramanujan, if that was a nice scenario, there was no world war and Hecke and Hardy were exchanging letters and Hecke actually opened Ramanujan's letter, that was actually surprising. It was so Ramanujan wrote to Hecke in Germany and he did not hear from him. It was later discovered among Hecke's papers after Hecke's death as an unopened envelope. So it's not clear what if Ramanujan instead of going to Hardy had been to Hecke, lots of things might have been completely understood then itself. Because a lot of work, the Ramanujan conjecture is a conjecture of modular forms which Hecke was working on. So there was lots. And in fact, there is another very beautiful thing that one of the first formulas about partitions which Ramanujan wrote in his letter to Hardy, Hardy took it and when he started proving it with Littlewood and all, they were able using complex analysis and all, they found that they couldn't prove what Ramanujan had this thing. So he said, no, there's a slight mistake and he gave a asymptotic formula with some error term and all that. And later many people took it and then Ramanujan's original thing was forgotten. But Rademacher, when he was giving a lecture again in 1937, full some 22 years after that paper was published, he, like any good teacher, did not copy. He thought, okay, this is the theorem, so let me go about proving it, maybe improve the notation, simplify things, etc. And he suddenly discovered that he did not have, he actually had an asymptotic formula with no error terms. And he presented as his work and this thing. And beautifully, it actually was the original formula which Ramanujan had written to Hardy. So because if Hardy was a number theorist, he would have seen that. But it took 22 years, and after Ramanujan was dead by then, to realize that Ramanujan's original formula was actually correct, and Hardy had this thing. So he knew modular forms, and of course the story that is romanticized, that Ramanujan did not know complex analysis. He did not know complex analysis in the sense that he could not answer straight and prove Cauchy's integral formula. That in that sense he did not know complex analysis. But nobody who does not know complex analysis can actually write such series and write identities. So he knew, but in a different sense of that word.
In fact, that's why Bruce Burt also remarks, do we really understand the thread of mathematics which he represented? And the other thing is, we keep saying that there's a lot of examples. Could it be part of, let us say, an old Indian tradition that the way we do things and state is not given to proofs often?
Yeah.
In that we say do these steps and this is what will appear, and here are some examples, and this is a way of logical presentation.
I completely agree with you. See, that is the Indian tradition. There is something called Brahma Sutra, 500 of them, which is just small statements of this kind. Janmadhyasya taha. Then they say, okay, you derive all these Upanishadic truths from that. So how does one do that? Again, you have various bhashyas of Shankara, Ramanujan, Madhvacharya and all. Similarly, you can take Ramanujan's 17 examples of Mock-Theta functions as sutras. Now you say, okay, what is it? So all these papers are bhashyas on that. So the Indian tradition is of that kind. You just let that high point and give, and what it means is for others to reveal. Yes, completely correct in that. Yeah. Thank you very much.